Uh, Dorit, do you, do
Yes.
you want me to try to run Umesh on emulation mode?
What is emulation mode?
I can.
No, I think he
No,
just
okay,
needs a
all
few
right, all
minutes to
right.
wake up.
You're shouting. Maybe the
Ah,
volume
okay.
is too high. Can you maybe show us your Hebrew, Scott?
Okay. בסדר. אז איך זה?
לא רע, לא רע.
אוקיי, בסדר.
I'm skeptical of your abilities to speak Hebrew.
כן, אני מבין את זה. איך אומרים, your skepticism is justified?
Does your ability to speak Hebrew, does your fidelity decay exponentially the longer you speak?
בדיוק.
Sandy.
It means exactly.
Yes. There is a special, it's Formula 7,
All right.
it's exactly that.
All right, everyone, and welcome to the panel on quantum supremacy that culminates this fabulous week of school that we've had. I'm going to briefly introduce the members of the panel. Sergio is going to start out with a brief overview to make sure everyone is on the same page. I'll start out with a few questions for the panelists just to get the conversation started, but pretty soon I'll open it up to questions from the audience. So you're free to come down to either mic and ask a question of any of the panelists if you like. So hopefully this will be an interesting conversation. So just to introduce the panelists who are here with us at Hebrew University, we have the woman who needs no introduction, Dorit Aharonov, who's put together this school for us. We have Adam Boland from UC Berkeley, Boaz Barak from Harvard, Gil Kalai, also from Hebrew University, and joining us from cyberspace, we have Sergio Boxel from Google. Hi, Sergio. Scott Aronson from University of Texas, Austin, and Umesh Vazirani from Berkeley, California, UC Berkeley. So,
Good morning, Umesh.
So, yeah.
Good morning.
Good morning to those coming to us from North America. Thank you for waking up so early.
You're welcome.
Now, each of the panelists brings sort of a unique expertise and perspective to this topic. Instead of giving more introduction, I'm just going to let it unfold, and those perspectives will become clear as we go along. So let's start with Sergio and his overview of the Google experiment and results. Sergio, I think you're muted. There you go. Yeah.
Okay. You can hear me, right?
Yeah.
Okay, perfect.
That's it.
Okay, can you see the slides?
Now we can.
Yeah, I can see them.
Yes, we all
Alright,
can.
good. Perfect. So I'm going to go very quickly over this. It's just a quick overview. So this is an experiment done by a big group of people. Here you have them, experimentalists and some theorists. And basically what we do is we run a random quantum circuit with up to 53 qubits and sufficient depth so that as far as we can tell, we cannot simulate it anymore with any of the available classical algorithms. And we did spend a lot of time working on classical algorithms and optimizing them and running them on millions of cores. So on the top right, you have the layout of the 2 qubit gates. As we step over cycles of 2 qubit gates and the single qubit gates, which are going to be random. Every single qubit gate takes around 12 nanoseconds. These are on superconducting qubits. And the 2 qubit gates are 12 nanoseconds. The single qubit gates are around 25 nanoseconds each. And then we measure and we repeat this many times. So we have this metric, which is an estimator of the fidelity that we obtain when running the full quantum circuit. To obtain this estimator of the fidelity, we need to do the full simulation. So as long as we can do that, then then we have an estimator of what is the fidelity of the full circuit. And when we cannot run the simulations anymore, we save the data, and all the data is online now. So if people can simulate more circuits than we were able to, they can just run their simulations and check the fidelity. So the first thing we do is to check the fidelity of the single qubit gates and 2 qubit gates. It's very important that for the 2 qubit gates, we are talking about the fidelity in simultaneous mode, meaning when we have 2 qubit gates on all the pairs of qubits simultaneously. So we take into account possible crosstalk. So that would be this green line over here in the middle, and this is the histogram. So there are not many outliers, and the average is 0.62% polyerror rate for every 2 qubit gate. So once that works, we run full circuits. We also run simplified versions where we either break it in half, those are the patch circuits, or we remove some 2 qubit gates in the middle, which makes our simulator a lot faster, exponentially faster. So first we run circuits from 12 qubits to 53 qubits at a fixed depth of 12 cycles of single and 2 qubit gates. So that's the graph on the left. And the fidelity from our estimator on the full circuits, those are the red circles. The largest circuits for which we did the fidelity are 53 qubits with 12 cycles that took around 5 hours.
So, sorry to
per
interrupt you,
circuit.
Sergio, but we're not
Yeah.
seeing your slide with the fidelities that you're talking about.
Oh, really? I'm sharing my screen.
Yeah, it was stuck on the first slide.
Oh, really? All right, let me stop sharing. Oh, I've been going through a few slides. Can you see anything right now?
Yeah,
Yes.
Is this good?
yeah. So we're seeing the slide quantum supremacy data.
Okay. Did you see a different slide now?
This
Or
is
the same slide?
simulation cost.
Schrodinger-Feynman algorithm.
Okay, good. So I just saw this slide before, which is the simultaneous 2 qubit gate fidelity, which is this green line here. And that's the 0.62% polyerror rate average for 2 qubit gate. Okay, so this is the data of the full circuit, which is figure 4 in the main paper. The paper is in Nature, but you can just see it. It's not behind a paywall. So the red circles, that's the fidelity that we estimate for the full circuits. The larger circuits we estimate the fidelity for are 53 qubits F12, and I was saying this took us 5 hours per circuit, approximately running on 1 million cores. So 5 million hours per circuit, and we had 10 circuits, around 50 million hours to get this point. If we break the circuits in half, those are the patch circuits. Those are the, we calculate the fidelity, of course, much easier because we only have to simulate these 2 smaller circuits independently. We saw that as these blue plus signs on the plot, and they overlap nicely with the full circuits. And we also have these elided circuits where we remove some of the 2 qubit gates. We still will have full entanglement on the whole circuit, but the simulation is much easier. And those are the green crosses, and they also overlap. And finally, the black line, what we do is we just multiply the entanglement fidelity of all the gates that we obtain independently on the experiment for the plot I saw before. And again, it overlaps with the fidelities of the full circuits and the patch circuits and the elided circuits. Okay, so that's the left panel. And then on the right panel, what we do is these are all circuits with 53 qubits, and we increase the depth from 12 to 20. We don't do the simulations for the full circuits anymore because this is too expensive. But we estimate how long it will take to do the classical sampling, at least with the best algorithms that have been implemented so far, on 1 million cores. And those are the gray numbers on the top. So our estimate for the largest circuits, which is 53 qubits step 20, on the fastest algorithms that have been implemented and tested so far, is around 10,000 years. Okay, so this is just a slide on the supplement about the simulation cost of the different algorithms. So what we call the Schrodinger algorithm is you just save the full wave function, and then you just keep applying gates to it. And the cost of this algorithm, as you can see, is polynomial in depth. So as long as you can store the full wave function, then this is probably what you want to do. And so far, people have only done this using RAM in supercomputers. So that's this line here. There is a proposal to use disk, but that hasn't been tested, so it's unclear if it will work. But if you can do that, then you will be faster. What we do instead is we do this Schrodinger-Feynman algorithm, which basically means you break the circuit in half and simulate both halves an exponential number of time, which is basically summing over all the possible combinations of Smith coefficients on the 2-qubit gates across the cut. And that scales better with the number of qubits, but exponentially in depth. So this is what we do for our verifications. And the panel on the right, that's how we get our estimates of 10,000 years for depth 20. Finally, this is what we say in the paper. I'm just going to read it. We expect that the lower simulation cost than reported here will be eventually achieved, but we also expect that they will be consistently outpaced by hardware improvements on larger quantum processors. We strongly support running validation programs, so we publish all the data, and eventually people might be able to simulate those circuits and check if the fidelity is what we claim. But it's important that we compare experiments and not just proposals, including in simulations. It's very important to run them. And it's tricky to run efficient supercomputing code and take into account failures. If you run on 1 million cores and if you want to use 74 petabytes of this, you're going to have failures, and that's going to make your program tricky. And eventually, we'll have sycamore processors with more than 57 qubits. So that's all I wanted to share.
All right. Thank you. So I'll start with a question for the panelists. And since you finished your presentation with a discussion on the simulation costs, I'll start with asking about, there was a bit of controversy after the paper original came out, IBM claiming that they could do this classical simulation in 2.5 days. What should we make of that statement and that claim? And any panelist can chime in.
Sure. Yeah, I'm happy to take this one. I think that from the complexity theoretic standpoint, what we were trying to prove about this experiment is we were trying to give evidence that it's exponentially intractable to simulate. But the complexity theory doesn't usually tell you, exactly what exponential time that would take. And the basic situation is that the IBM paper proposed a different exponential time simulation algorithm. So in some sense, the fact their simulation algorithm takes exponential time, or in this case, exponential space, it only bolsters the case of the difficulty of simulating the experiment.
Any other comments?
Yeah,
Well, I mean, should I
Can
go?
I just talk? I want to I just want to have a friendly nudge to Sergio about the data that in order to verify the computation, the probabilities for the ideal circuit should be uploaded to the system, and the probably this is not the highest priority, but this would be very useful. So, Sergio, this is a friendly nudge for you. Okay?
Yes, we're working on that. Up to 30 qubits is not so hard to just calculate the probabilities, but yeah, we're working on uploading all the probabilities. Sorry, we're a bit delayed on that. As you know, we've been on an
Okay,
English chain.
thanks a lot. This was a friendly nudge. Yeah.
All right,
So
Scott.
Actually, sorry, quick question following up with Sergio. So, in your description, could I was a little unclear which was what was the highest number of qubits on which you simulated the depth of 20 some?
So we didn't do, we did simulations on 53 qubits depth 14. That's the highest depth.
Yeah, but what about smaller numbers of qubits and depth 20 something?
I mean, we have done it, but we didn't run the experiment. It's easy to run, 38 qubits depth 20. That's easy to simulate, for instance. But on the experiment, we did depth 14 from 12 to 53 qubits, only depth 14.
Okay.
Scott, were you about to make a comment? Did you?
Oh yeah, I was just going to say the analogy that I like for the IBM thing is one that I actually learned from Boaz, which is that it's a lot like the Kasparov versus Deep Blue chess match, except with the enormous irony that IBM is now playing the role of Kasparov, right? So we're like entering an era where with heroic effort you can indeed match what a quantum computer is doing on random circuit sampling with a supercomputer. In this case Summit, literally the largest supercomputer on the planet, right? And the crucial point was that it has 250 petabytes of hard disk. And so their proposal was basically to just, IBM's proposal was to write the entire state vector to hard disk. And they say that this could, you could just do the matrix vector multiplications and do everything in a few days, which indeed, as Sergio said, they have not demonstrated that, but it looks plausible that indeed can be done. It's also clear that this is not a scalable approach, right? And so, people have, I've heard a bunch of people quibble over the exact definition of quantum supremacy. And well, does it count if there's still one supercomputer on the planet that can feasibly do the computation, right? I don't care as much about that. I'm more interested in, are we really entering this era or aren't we?
All right. So error correction will certainly play an important role in scalable quantum computing, and a lot of the theory of error correction depends on an independent model of errors. So do the Google results shed any light on whether this is a good model for errors in quantum circuits?
I can say something about it. Well, first of all, indeed, in some aspects, there is some remarkable independence in some of the errors that we may come to next. But when it comes to correlation, for the sake of error correction, these random circuits are not so relevant. So if we have concerns about error correlation that increase the qubit errors and make it harder for error correction, then this has no bearing at all on the for random circuits. I should say that one thing that the Google experiment does confirm is that the effort we need in terms of lower error rate for quantum error correction is harder. We need lower error rates to achieve error correction compared to what is needed to achieve quantum supremacy.
Can I say something?
Yeah, sure.
Okay. I mean, I would say that if this experiment had not worked, or if it had not been possible to get the fidelities low enough to do quantum supremacy, then that would have been a severe problem for quantum error correction, right? I mean, so I think that doing this is sort of a maybe not a logically necessary condition, but in practice a necessary condition for getting to error correction. It shows that there's no unexpected obstruction along the way, at least at the level of integrating 50 or so qubits and, getting them to apply a random circuit.
So, can I jump in? I thought I would like this to present sort of a picture, and I might be wrong, and I'd be happy to hear others comment on that, especially Sergio. But I want to sort of place it on the table. So, in my opinion, there's sort of two different questions. One is whether quantum mechanics in the ideal world holds. If we could just get rid of all noise and make everything ideal, is quantum mechanics really, does it follow the quantum computation model, and can it achieve supremacy? And but even if we put as infinite effort, as much effort as we can to get rid of all the noise and put it in temperature 0. And the other question is whether if we add noise to the system, does it still hold? Does the disadvantage still hold? And I think these are two very different questions. And I think until this experiment, we had very little evidence for the first question that really are, not very little, maybe I was exaggerating, but we had much less evidence that in the high complexity regime, without any noise at all, the system is capable of performing, of following the quantum circuit model. And if we believe what seems to be, I don't know, a very strong belief that quantum computers, the ideal quantum computers, the mathematical model can actually do things faster than classical, then this is amazing. But then this is a different question than what would happen when we add a little noise to the system. And so basically, if we know the first, if we validated the first claim, we're sort of at the same stage as we were before the threshold theorem, before we knew that if we add noise to the system, we could handle it and still maintain the quantum advantage. And that seems, I don't know, that to me the Google's experiment is remarkable in that sense that it actually probes this high complexity regime. But then the question is, does it probe it also in the presence of noise, and does it actually give evidence that with the noise that we have in physics, that we will be able to achieve quantum supremacy or exponential advantage as n goes to infinity. And there, it seems that to me, and I may be wrong, I don't really know the details of this experiment, but to me it seems that the evidence for that is weaker. And in particular, the scaling of this experiment so it doesn't scale for two reasons, right? The verification is exponential, but also the error the fidelity becomes exponentially small as n goes to infinity. So it seems that these two regimes, these two questions are different in the way the Google's experiment approaches them. I'd be happy to hear what people think about it.
So I just, I think that there are two different things. One is, do we already have good evidence that we can build quantum computers that can do something that could not be done classically, that have exponential speed up for some tasks over classical algorithms? And I think the Google experiment is really a very strong suggestion that this can be done. There is no inherent barrier to do that. There is the second thing is, can we completely realize the full mathematical capabilities of BQP? And that's maybe, and that might require, again, it's very promising, like Scott says, if they hadn't, they managed, I guess, to get each gate down to, 0.5% or something like that, they have managed to get each gate down to be fairly reliable. It's not yet enough to, to get full quantum error correcting codes, but it's not completely out of the ballpark. But I would just say that we need to separate the two things. I think evidence for exponential speed up and violation of extended charge Turing is fairly strong. Evidence that we could fully simulate the mathematical models of BQP, that may be weaker.
But isn't evidence for violation of extended charge Turing thesis the same as the first thing?
No, you could imagine a strict subset of BQP or complexity classes for sampling problems, or strict. You could imagine a situation where you
Yeah,
have like say something that lies between BQP and P.
Okay, so I have to disagree. I think there are three classes, sort of. There's a BQP complete, there is something in between, and then there is the noisy era, which may be not asymptotic.
Yeah. I think that the challenge here is that our best evidence for these kind of quantum supremacy experiments being hard in the asymptotic regime still requires error correction. Like these average case approximate sharp P hardness arguments, or also the Hogg style arguments really make the most sense when you get asymptotically a constant score on these tests.
I mean, Dorit, I think that you are raising a subtle point here, right? Which is, why can we draw asymptotic conclusions from these experiments if no one expects that these experiments will scale asymptotically without error correction? So I think we ought to be clear that the only, unambiguous experimental demonstration that error correction is possible will be to demonstrate error correction.
That's
right?
true.
Right. That's that. But having said that, what I am interested in with Google's experiment is, is there a way to explain the results of the experiment without making reference to, say, the actual reality of a superposition state involving 9 quadrillion amplitudes?
No, so I think that, okay, so this, sorry, I'll just answer, and this is something that I think that there is no way to explain that, and for me this is very strong evidence that nature actually behaves on the large scale in the high complexity regime of quantum mechanics. But I don't think that the only way to test whether it's possible to, to perform quantum computation asymptotically with n goes to infinity, that it will work with error correcting codes is to demonstrate error correcting codes. For example, I would like to see evidence that the noise model at large n limit behaves nicely as we would have as we want, according to the threshold theorem or the assumptions of quantum error correction. And to me, I think that I maybe I'm wrong here, but I think that Sergio's experiments are fully consistent with a model in which indeed which qubit or which gate is faulty is picked independently at random, but then if something happens to one qubit, the whole system goes astray and becomes completely random. In fact, their model follows this description. So meaning like when there's error, then they replace the whole thing by an identity. So and that model is, of course, is not good enough for fault tolerance. So I'm not saying this is a model that's reasonable, but I'm just saying that these experiments, I don't understand yet what they tell us about the noise.
So if I may say something about, so there are a few different issues that come up there, right? One is how, just how convincing is this as a proof of supremacy? So I think, I would say I would be slightly more cautious than Dorit on this, Dorit, in the sense that I think that it is convincing, but I think that I think that quantum supremacy is not just a point; it's a it's a continuum, and it's a little bit more analogous to the Bell experiments, where you do them better and better over time, and there might be people who are already convinced, and there are people who will be convinced later. There are different thresholds for being convinced about this. In terms of errors, I would say that there's again two different ways you can look at it. One is you say, well, we can be working in the regime where the gate errors are of the order of one. That the error is of the order of 1 over the number of gates, and in that regime you don't need fault tolerance, right? So now you could say, well, does this, is this asymptotically going to work? Well, it depends upon what you mean by asymptotically. It could be that as you increase the number of gates, you also work harder to make the errors smaller, or you try to say, well, we are not going to be trying to make the errors smaller, but we'll actually fix the errors at some level, and then try to move forward through fault tolerance. So you could go you could work asymptotically in one of these two regimes, and that would be fine. But then there's this third issue, which is, does this experiment actually characterize the model for errors? And I think that there was some suggestion in the paper that it does. I was somewhat skeptical about that claim that it does characterize the errors, and in particular, I think Dorit's summary of a model that's consistent with the results of the paper. I mean, that sort of puts it in perspective. I think that there are many models that are consistent with the results, and so, I think one would have to work much harder to actually characterize the error model through supremacy experiments. But the fact that one might be able to is actually a great possibility. The fact that in the future, as supremacy experiments are refined and made more interesting and in various ways, that this might be the route to actually characterizing the error model. I think this is a great possibility.
Let me mention, I'm losing my voice, that one interesting aspect of making together practice and theory in computation and complexity, not necessarily in the context of quantum computing, is some assumption of naturality of the constant involved in the algorithm. And therefore, we do regard a very high exponential behavior for a small number of qubits as demonstration of supremacy, because we don't believe that this represents some high degree polynomial. And this naturalness, which is similar sort of to naturalness in physics, which is a sort of a meta principle, a useful meta principle, is a good guideline. And as far as quantum error correction and quantum supremacy, so as I said, I completely agree that quantum error correction, there are several indications, some theoretical and some empirical, that quantum error correction is harder than demonstrating quantum supremacy for this noisy intermediate scale quantum systems. And in fact, this distinction or this observation is quite central in my own work about why quantum error correction cannot be achieved. We will come to that.
Okay. Can I just directly address the point that Dorit raised? I think that one of the most significant reported findings from the Google paper, besides just quantum supremacy itself, was indeed that the overall fidelity of the circuit, is more or less what you would expect it to be from just multiplying together all of the fidelities of the individual gates. It's of the same order, right? So that's, on the one hand, you could say that's bad. It decays exponentially with the depth. In the case of Google's hardest circuits, the fidelity was only like 1/500. Okay, but on the other hand, as long as the fidelity doesn't decay any worse than that, then there ought to be no obstruction to eventually doing fault tolerance.
No, that's not true. Like in the model, that's not true. Like in the model I offered before, where the fidelity decays exponentially because if you put errors IID on each gate and qubit and every time step, and then if there's an error, everything explodes, or everything is replaced by a completely random circuit, that does not allow fault tolerance, but the fidelity decays exactly as we would expect.
Well, they didn't observe their device.
This is because there is distinction between the fidelity estimation for noise and the noise in terms of error, the number of qubit errors, and indeed this distinction does not come to play in the random circuits model.
Yeah, so this is true that the data. Oh, sorry, Sergio. Go ahead.
Oh. Sorry. Yeah, I just wanted to say about the errors. We run different circuits on the same qubits. It's just changing the controls. The complexity of the state is very different, but these are different circuits run on the same qubits, right? So in particular, we run these circuits which are just 2 qubit gates being applied to different pairs of qubits. That's how we obtain the error for the 2 qubit gates. And when we do this experiment, and we're doing experiment on all different pairs of qubits simultaneously to obtain the error for the 2-qubit gate. This experiment is incompatible with the model that you suggest, right? Because if we had an error in a 2-qubit gate and it, destroys the full state, then we wouldn't get, the error rate per 2-qubit gate that we obtain. And now we take these numbers, which is, on the same qubits, and we apply them to the, we multiply them and we get the same fidelity as the full circuit. And the same when we break the circuit in half, right? So we run both halves in parallel and we obtain the fidelity for this half and the fidelity for this half, right? Again, if we had an error in one half and it propagates to the full system, we wouldn't get the numbers that we get, and we multiply the fidelities and it gives the same fidelity as the full circuit.
Yeah, let me just clarify. This was just a toy model. I'm definitely not saying this is what's going on in the real world, but yeah, I guess that there are other models of error that would fit this the behavior. I don't know of them, but I'm guessing that.
Yeah, exactly. Yeah, I see that suggestion as more something to provoke you to think of different error models. Of course, there is some sort of like Occam's razor consideration. So, clearly a model where, if there's an IID choice for each gate, and then your computer explodes in a powder of dust in your lab is clearly not what happened. So the real question is if there's also kind of a very simple error model that looks natural in some way that gives rise to correlated noise, that would also reproduce the same results.
Right, while we're on the subject of noise, did you want to present your slide? Are we?
Umesh disappeared.
Okay, so this is a single slide event. Initially, I prepared a longer presentation, but this was done offline. But I think one thing that we miss in this discussion is, of course, it's important to think if what are the implications of supremacy? Is it useful? What it says for the Church-Turing thesis? What it says for quantum error correction, for the prospects for universal quantum computers, for factoring. But I think, at least in the next few years, one thing that we need to concentrate also is the Google experiment correct? Is this a correct scientific verification of quantum supremacy? Indeed, I want to refer to the same thing that Scott referred before, and this is another remarkable discovery of the quantum Google paper, and this is a formula. The formula itself is not surprising. It's a high school probability, but the performance of this formula is very remarkable. And the formula is that the fidelity can be computed as the product of the individual fidelities of the qubits and the gates. And as a matter of fact, and the remarkable thing is that this gives you the predicted fidelity for the whole circuit up to 10 to 20%. So the whole circuit is built from something like 1,000 quantum gates, as written here, tens of qubits. You take the product of all these numbers, and this gives you the actual fidelity as shown by the experiment as the fidelity of the circuit. And in fact, you can even use this simple formula, 1 minus 0.038 to the power n times 1 minus 0.016 to the power g1 times 1 minus 0.0063 to the number of 2 gates. And this will give you, again, the fidelity for the whole circuit, maybe up to 30% errors. And this type of behavior, this type of prediction seems too good to be true. The idea that you can predict in such precision the fidelity of 1,000 elements experiment as the simple product of 1,000 numbers, to me it seems like unbelievable nonsense. And this is something which we should, at least this is intuitively, of course, there are theories, people study this type of fault tolerance or reliability of systems, and at least it seems that this is very remote from what we see in physics, and also the graphs that demonstrate it, including the graph that Sergio showed, and the graphs which show how the various type of experiment match perfectly seems to be too good to be true. And I should say that in a scientific experiment, if the data fits the theory or the model too good, then this is also a bad sign.
Okay, so maybe we can let some of the other panelists comment on this. Any?
I mean, I would love to hear Sergio's comments on it, but I mean, Gil, I can't help but feel that if in some other universe the data had not matched the theoretical prediction, that you would have been calling attention to that as as anomalous and a big problem in need of explanation.
Yeah.
All right.
I also want to hear Sergio, but in particular, one kind of nice question which probably Sergio could answer is it really so unbelievable? For example, if you multiply 1,000 numbers and I guess suppose you have an estimate of them plus minus delta, maybe you would expect that the error that you accumulate is something like square root of 1,000, which is about 30 times delta. So how good are your estimates of the individual gates success? Is it believable or not believable that you get this kind of accuracy?
Right. Let me just interject. Well, let's hear from Sergio, but we'll also open it up for questions from the audience soon, so people can start to come down, approach the mics if they want. But we definitely want to hear from Sergio on this. So.
Yeah, I think what you said holds. You multiply by the square root of the number of gates. I think the precision at which we estimate the error of the different gates is, some small percentage. And if you do that simple back of the envelope calculation, then it's consistent with the, 10 to 20% error for the full formula that we see. And there are different fluctuations, but we actually, that's just what we see in the data. It doesn't, we look like circuit by circuit for the different sizes, and we haven't seen any problems so far. And it's consistent with this simple back of the envelope calculation. Yes, the square root of the number of gates with the precision that we get the fidelity of the different gates. And I agree that this is very remarkable, and so we think this is one of the biggest findings so far. I think if this wouldn't hold, then we will be more skeptical about the program of fault-tolerant quantum computers. But given that this works, then we're more optimistic.
No, I think this model is not necessary for fault tolerance. I mean, this is a very specific model. I think we shouldn't be worried if there is a slightly different model. There are many models. As long as the decay of the correlations goes fast enough, we should be happy.
No, yeah, I should add this wonderful prediction of the fidelity is by no means necessary for building quantum computers. This was only necessary for the complicated logic for the supremacy argument. But if you want to build quantum computers, all you need is that you have upper bound on the fidelities. And if the fidelities are lower, this is even better. So what is unusual here is the precise estimation. This is not needed for quantum computers. It is needed for this complicated supremacy argument, which do a very wild extrapolation. And I think a very interesting question is what happened in the IBM quantum computers. If for them the 10 to 20% is replaced by 20 to 30%, then this is believable. But if it is replaced by 3,000 to 4,000%, then I would say this is a reason to raise the eyebrow.
All right, do we have questions from the audience?
Or more comments from the panel.
Or more comments
Abroad.
from the panel, yeah.
feel like
Well, this,
first the data is not good enough, then the data is too good, and it's like a comedy routine. Like, what can the data do that will make you happy, Gil?
Yeah, I think this is a good question. I think the data should be reliable, and this is a very crucial ingredient in a scientific experiment. Actually, this is a question that not I should have asked, but the referee of the paper. But this is the non-anonymous. Actually, Scott was the referee of the paper.
Well,
I
I was
think
one
I
of the
think
one of the three.
I think it's a well-known uh, problem if the data fits the model in an overly good way. It's not something that I introduced into science, and you can look it up.
I mean, I thought usually the whole point of physics is that in physics the data usually does match the model very well. So this, I know that we're probing a kind of new place in Hilbert space, but I don't see the data matching a model
No, but-
being a problem unless you think the data is incorrect for some reason.
No. But you see, the data fits the model only if all the individual errors are unbiased. So if there are systematic errors, this will make a huge difference. And there's no reason to assume that there is no systematic errors. And also it assumes complete independence. And there is no reason to assume there is complete independence. As a matter of fact, the numbers that are used are numbers which are based on dependence. So they have two numbers for the two qubit fidelities. One when they work alone, one they work together, and they use the other ones which are in the case of dependence, and then they multiply them. So this is a very, very, very delicate issue. So I wouldn't say that in physics, this is, but okay, give me example where this in experimental physics. And also what happened in the IBM, can they do something similar?
Let me just say, I don't know if that issue is the main thing, but it might have something to do potentially with the fact that you're running a random circuit on a random input. For example, if you are classical gates and you had gates that say fail with a different probability, if their input is 0, 0, then their input is 1, 1, then you might have situations where the probabilities don't multiply, but if you're running them on random inputs and running something like a hash function where maybe, first of all, the marginal that you get into every gate is uniform, and the second thing is that once you screwed up one gate, there is no recovery from that, then you might end up with a similar situation where the probability of failure is the product of the probability.
So show me something formal, I look at it. Yeah, thanks.
So I would like to say, we don't only compare the full circuits with this model. We have also other intermediate steps where we cut the circuit in half, and they also agree, and we remove just some gates in the middle, and it also agrees. And then we have two types of full circuits. One is simpler than the other, and everything agrees. So it's not just a comparison of full circuits with this model. There are also the intermediate steps, and as far as we can tell, everything is consistent.
Okay.
I'm curious to hear what else. I mean, Sergio, what else are you testing there? Like you said, I don't know. I heard when you said that there are lots of other things to test. What would you test?
What did we test in the experiment?
No, what would you in the future? What are you going to test with respect to noise?
Oh, in the future, we're going to be working, for instance, on error correction experiments, surface code kind of experiments, decoding, and a lot of calibration and metrology. I mean, of course, the experimental group and we have a core group of physicists just working very carefully on calibrations, and there are hundreds of experiments. I mean, just to calibrate the system, it runs, like 100 or 200 different automatic experiments before we even start running circuits, right? And we have a lot of people working on calibrations of gates, but eventually we will, be working on experiments related to the surface code and doing, decoding error corrections, repetition code, and that will give us more characterization of errors. And things like simultaneous randomized benchmarking, where you can try to look at correlations. When you're doing decoding on the surface code, you also get estimates of the correlated errors because you're decoding, and you can see when you're decoding what percentage of correlated errors you tend to see in the system. So there's a lot of work to be done, yeah.
Sergio, can I ask you a question? So now that this is done, how do you think the amount of effort is going to scale, is going to scale as a function of n, the number of qubits, and, let's say epsilon, the error per gate? So if you want to, double the number of qubits at the same error with the same amount of error, is that a matter of a few months, or is that a really long slog? And similarly, if you want to double the number of qubits and as well as halve the error rate or decrease it by a lot, how does this look going forward?
So I think that the error rate should still decrease exponentially as a function of time. So maybe, I don't know, maybe you can have the error rate every 2 or 3 years to some point.
Sorry, you can hardware what?
Yeah.
Have.
Half the error rate every 2 or 3 years. And I think that's what, we have seen consistently in the history of superconducting qubits. And doubling the number of qubits, it's easy to print more qubits in a circuit. At least at these scales, and get the number, 2000s of qubits, I guess. The difficulty is the whole control system and cabling and all this stuff. But I think in principle, we could also double the number of qubits every, 2 or 3 years as well. So I think the priority now is to lower the error rates more than to increase the number of qubits. And it's actually a bit harder. But we don't see any reason why we couldn't achieve, half error rate every 2 or 3 years.
And is there correlation between the two? So if you double the number of qubits, is maintaining the error rate, does it become harder, or are these independent variables by now at this scale?
Well, there were, to get to where we are, the experimentalists had to go around a couple of technological challenges. For instance, going from 1D to 2D was very hard. They are now using bump bonding, so instead of one chip with controls coming from the sides, because it's a 1D line of qubits, now you have 2 chips with bump bonding and the control on one chip. The design of the qubit is different. All qubits have 4 connections instead of 2, which tend to introduce more errors. So to go from 1D to 2D was hard. That's why it took 3 years. But now that you have 2D qubits and you have 54, it's not in principle too difficult to just scale it, and the errors should not increase too much as you're scaling up. But what we want to do is actually to decrease the errors before we scale. Yeah.
So I have a question, actually taking up on what Gil said before. So it is, if I understand correctly, the model of noise that you feel that describes very well the system is really IID, random unitaries acting on each element that is faulty. And this is a very, very ideal model of noise. And it's really something that is hard to believe that it is really the right noise model. And I would suspect that the reason that it looks like this is the noise model is because you are talking about random circuits. So somehow the average of this somehow the deviations from this model are canceled out by averaging over the circuits in some way. And I would expect that there would be, for example, inaccuracies in the gates, which are non-unitary, not random. I mean, there are many noise models which are non-random, which are just not random. And in order to move to computation, you no longer have the assistance of randomization over the circuits. So I would be happy to hear your comment on that.
No, that's true. I mean, there are indeed all kinds of errors, and there are correlated errors. But indeed, because we're running random circuits, we uncorrelate errors. And I will say you need to do the same thing when you're running other more structured algorithms. So you always need to be very careful how you run algorithms. You need to introduce randomization or gauges to break correlations. But if you do that, and if we can do that well enough, then you should be able to see similar performance. If you don't randomize your errors, then you're going to see worse performance because correlated errors are going to act coherently, and they're going to impact your fidelity more. We are not claiming there is no crosstalk whatsoever. I mean, that's part of the difference. I mean, we're very clear that there is a difference between if you measure the fidelity or the error rates of 2-qubit gates in simultaneous mode when you're running 2-qubit gates on all the qubits, or if you're running them just a 2-qubit gate when all the other qubits are in the ground state, the fidelity gets worse, around twice worse. And that's because as the neighboring qubits are sort of excited, they change sort of the Hamiltonian evolution because there is always a little bit of crosstalk. But the point is that, when we measure in simultaneous mode, we're sort of measuring that crosstalk as well. And when we run on the random circuit, then we randomize all those errors properly. But the crosstalk cannot be a model in which an error somewhere introduces an error in the full system, because then when you measure in simultaneous mode, you will then see the 2-qubit error rates that we see. So there is some crosstalk, but it's local, and we just measure that by running simultaneous 2-qubit gate benchmarking. And it's very important to do benchmarking in simultaneous mode, because indeed the crosstalk, it's very hard, and it's very hard to solve. As a matter of fact, something that also had to be done to get to the supremacy experiment was to completely change the model for the coupler. So we had Brisilicon that had more qubits, but the coupler was not tunable, and the crosstalk was just too hard to control. So we went to less qubit, but more control lines, so the couplers are tunable, and it's, you can switch off the couplers, not completely, but well enough so that you don't introduce crosstalk when operating in simultaneous
So
mode.
errors that you introduce into the system with a trigger link, with randomization, do not bother you. They're of second order.
Yeah, I mean, they uncorrelate. So, it's sort of the, best possible situation.
Let me.
And that's very important to run algorithms. You certainly, I mean, you should never run an algorithm without doing some sort of spin echo or dynamical decoupling or randomization or gauges or something along those lines. It's just not a good way to run experiments.
Let me mention two things about error models. One thing is that a very nice toy model is the one which we use quite often in combinatorics, just to decay the high terms Fourier coefficient, or in other terms, just to average the value of the probability distribution in a point with the neighborhood. And here we can also add the effect of positive correlation. And for this model, and probably also for the more realistic models, if you apply it on the random circuit, it doesn't make any difference. So this strengthens the point of Dorit and Barak on this matter. Another thing is that, again, as Sergio mentioned, the number 0.062 already takes some correlation, some dependence into account. And this adds to the mystery of the amazing success of the product formula, which is based on independence.
All right, let me reiterate the invitation to the audience to come down and ask questions if you have them. You've been so active in asking questions all week, so don't be shy now. The question wasn't said into the mic, but I can repeat it. Why 53?
Instead of 54.
One of them
They
didn't
were-
work, right?
There are 54 qubits in this particular chip. The main reason being the packaging and cabling. So we had the package and cabling set up for the 72 qubit Bristlecon. But the Sycamore, which is this chip, requires now one control cable per coupler. So that's why we had to go down to 54 to be able to use the same packaging and also control the couplers. And the reason why it's 53 and not 54 is one of the cables actually didn't have a good connection when they cooled down the chip the first time. But it was sort of the first try on this new Sycamore 54 qubit design, and they thought it wasn't going to work too well. And they didn't have another cable at hand, so they just cooled it down and it just worked great. So they didn't want to, we just run to the experiment instead of warming up, changing the cable, cooling down, replacing. So the problem was really on a cable. It wasn't the qubit.
So you saved IBM 250 petabytes by this change, right?
It's one cable.
So I have one remark, also suggestion that one concern that several people had, actually me and Ryan O'Donnell, is that we don't have enough experimental outcomes of the full noisy distribution for small number of qubits. So usually the samples are fairly small, so they are enough for this fidelity statistical test, but we would like to understand how the noisy model behave. And I think, again, as I said, there's much, well, actually I didn't say it, but there's much more experiment that can be done in the classically tractable regime that we would like to see. And right now we have only some histogram from some old experiment on a different computer with 9 qubits, but it would be very interesting to have large samples for 10, 12, 14, 15, 16, and so on, 20 qubits, 22 qubits, large enough samples that we can actually understand what is the distribution of the noisy model. I should say that there, it's very interesting. We understand the first order behavior of the noisy model, which is simply the ideal model times the fidelity plus 1 minus the fidelity times the uniform distribution. But we would like to understand the lower order term. And this is quite important to several of the issues that people raised here. And this is a kind of experiment that can be done with a small number of qubits.
Sergio, you're on the video now.
Sure, yeah, no, I agree. I mean, we're certainly, as I said, there is, a fair amount of people working at Google on doing many experiments trying to calibrate noise. And yeah, and, there will be more papers following up with better characterizations of noise. And some of those papers are maybe just like 1 qubits or 2 qubits. I mean, you can look, there are papers on just, a couple of papers just looking at the TLS, right, which is a very important source of noise. So there are, very detailed experiments looking at, the dynamics of two-level system noise and the distribution of two-level system noise. And yeah, but, working on noise characterization and improving noise and calibration is indeed something very important.
Gil, I have to say that you're a little bit like this old joke. You're saying the data is too good to be true, but there is also too little of it.
Actually, this is true. These are two different concerns. I mean, the too good to be true is a sort of a serious concern about what's going on. The fact that the data is too small, I think if we want to check, if we don't just have a one-track mind to the supremacy, we want to check what is going on. It's very natural to supply a large sample. So I don't think that this is a contradictory piece of criticism.
Sorry, but isn't this already, data that's existing? Sergio, isn't that data that you can provide already for the 22
So this is
Maybe
what
not.
Ryan and I were asking repeatedly. I don't know if they have enough samples, but maybe they do. It's just we are waiting for the full data, and we will see. But I'm not sure there is enough samples, even for small values of n, beyond what is enough for the statistical test. But maybe there are. I mean, this is not one of the problem is that we still don't know if there is enough data for the full histograms, or there isn't, what precisely.
Yeah, I think, all the beta streams are already online, I think. And I think you're waiting for the probabilities. For 20 qubits, you can just run the circuit on Circ, and, Circ is open source. And
Where?
you already have.
I can run the circuits where?
Circ is our, open source platform.
Oh, you have open source for your circuits. So, because
Yes. With 20 qubits, that's easy to do. But we're putting all the probabilities online.
Okay, yeah, I mean, actually, and the open source is reliable. It gives precise. Yeah, I know. To go, well, if you want to verify the Google experiment or to analyze the data, I think the first thing is to look at the paper. There are a lot of things you can learn from the paper and the supplement. The second level is to look at the data and the probabilities. And then the third level is to run your own circuits. I think on the level of programming, this is harder. But if there is a reliable open source that will, then this is certainly something that can be tried. And of course, the fourth level would be to run your own quantum computer. And this will be a little bit difficult.
But actually, Gil, I should comment that I would very, very much like for this experiment to be replicated. Not only to, increase our confidence about quantum supremacy as a whole, but also so that we can get more data. Like, what does anything happen differently when we try to do this in trapped ions or with neutral atoms, right? Does the error behave differently, right? Just can we show that the result can be replicated in those other platforms? And I very much hope that we're that people will not just abandon this, but that we're going to see that in over even just the next year or two.
Okay, I agree. Just take a note that Scott and I completely agree. And this is a historical moment on this, just on this sentence. Replications are crucial. And I even would say I don't mind about a very large number of qubits, but for small number of qubits, for 20 qubits, 30 qubits, we need replication both for the supremacy claims and for the precise prediction of the fidelity claims, and both for superconducting qubits and ion qubits and maybe other platforms. Good.
I think replication is very important, on other platforms, and I think this is a very good tool to diagnose crosstalk. And as I said, we had to change the design of the circuit and use tunable couplers because we couldn't control the crosstalk well enough to perform this experiment. So it's a hard experiment to do, and it's a very simple way to diagnose the amount of crosstalk you have in the system. If you have a lot of crosstalk, you are not going to be able to, do this experiment successfully.
So, Sergio, in terms of prospects to the future, it seems like you're saying in 4 years we'll be below the threshold, and right? Below the accuracy threshold or less. And in terms of using fresh qubits that are required in order to do quantum error correction, it seems that this is much closer, in your opinion. So do you see any problems ahead?
Maybe I'll add, what about distance Swiss surface code? Do you think you are close to achieving that? This is only 20, 25 or 30 qubits.
My understanding is that, there are, people working on that experiment right now, experimentalists and Austin Fowler and, quite a lot of people. We do not have right now the error rates that we would like for the surface code. But yeah, it's ongoing work. I mean, we don't see any fundamental roadblocks, but then of course, it takes, we want to get 3 nines Control C, right? Fidelity working on simultaneous mode. So that means we need to lower our error rate by a factor of 5. Not just halve it, but so that's very hard. I think we can do very interesting experiments on the surface code before we get there. I mean, we don't think there's fundamental impediments to get there, but it's of course very, very hard.
But in terms of bringing fresh qubits and cooling qubits all the time that is required for error correction, is this something that's, I mean, right now your setting is very different from that.
Yeah, and again, there are also people working on that, and they've been working on that for some time. Again, there are not fundamental problems, but it is very difficult. So it's somewhere in between. That will probably be experimental data out running error correction without using fresh qubits, where you just do 1 or 2 rounds and then you measure, and that's good enough to sort of do the statistics on the errors and the decoding without introducing fresh qubits. It will take a bit longer to be able to introduce fresh qubits dynamically and do repeated measurements.
All right, so I think we have a question from cyberspace. Is that right? Okay.
Yeah. Hi. I don't know if you could see me. Yeah. So I guess this is, I'll rephrase a question from Todian Mishtaku. I hope I pronounce his name correctly. So, Gil, right, it's kind of, I guess it's for all of you, but Gil emphasized the importance of equation 77, like the behavior of the fidelity as a product. And it wasn't entirely clear also in Gil's previous talk and now whether it's just something that you observed from the data, that it fits that very, very simple model, or whether there's a way to derive it assuming some noise model. And in particular, would it also be derived from Dorit, like the noise model which Dorit mentioned, in which you have independent errors, but then once there is an error, you replace everything with the maximally mixed state. And actually, this is a side comment. I think even if the answer is no, that there is no way to derive it, I think it's perhaps even the first case where you could actually form a conjecture based on, like, we didn't have this equation before, right? So this is really interesting to point out, is that maybe the first time where we have, something for theorists to work on and try to derive based on real-world data that we wouldn't have had or wouldn't have guessed without it.
I'm really having trouble understanding this equation as mystical. It's to me, this equation is just the first thing you would write down, and that you would just expect to be true unless there is some special reason why it's not true.
The equation is not mystical. What is mystical is the amazing performance of the equation, and the amazing performance is based, indeed, there is a statistical reasoning, but it's based on all the errors being symmetric, so there's no biased errors, and it's also based on complete independence. And these two assumptions, especially, and it's also based on the quality of the initial estimate, so this 0.0063 must be true up to 20%. And all these 3 assumptions seems unrealistic. So errors can be biased, and complete independence is not realistic, and therefore, and I think there is a whole theory that answering our question. We have here a situation of a physical system that once one of the elements has an error, then the whole system ceases to work. And there is a whole literature in engineering and statistics about this type of behavior, both theoretically and empirically. Of course, the product formula is the first thing you would guess, but then to try to understand how well it's behaved, this is a big theory, and this behavior seems unrealistic.
All right.
So I would like, first of all, I think a little historical moment that I have to agree with Gil on this point. I think it doesn't make sense really that this formula holds for every quantum circuit. I think, meaning there's no reason why you wouldn't have inaccuracies in the gates. Of course you do. This formula talks about something which is completely probabilistic, completely random. It's really too good to be true for a given circuit. I think that in the experiment that Google is running, there is probably a good reason to expect that on average, this model works and that the deviations from this model somehow on average are okay. But I think that for a given circuit, if I give you a particular specific quantum circuit, and you would tell me that the model is really completely random and no correlation between the different qubits and everything is perfectly independent, and there is no inaccuracy in the gate that is somehow directed in one direction, it's very surprising. Just, I don't know, it's just too ideal.
So Doreen, can I ask a question? So I'm slightly losing track of this discussion. So is the issue that's being discussed just the fact that the errors are independent, or the fact that eventually with these random circuits you get the assertion is that you get a convex combination of the uniform distribution and the true distribution with probability, which is a product of of one minus the errors.
No, we discussed the first issue. The second issue is also interesting, but this is a good approximation. We discussed the first issue, whether the fidelity is the product of the individual probabilities as estimated by the Google team.
So, I mean, Gil, we've discussed this in the past, but if there are variations in the errors themselves, then we should expect that to be only a second order effect, because those variations will almost all cancel out when you multiply.
No, because only if these variations are symmetric. But if there is systematic variation, then the effect is much larger. And even this is under independence.
Let me ask Sergio something I don't know, and with respect to your experiment. If you have a model which is not completely ideal, like random, independent, etc., for every circuit, but somehow over the circuits the model of error is randomized, do you not get the same formula? Would you not get the same results? Is the question clear? So I would expect that for every circuit there would be some different deviations from the truth, but that some with decay of correlations, but maybe not as ideal and then averaging over the different noise operators over the different circuits. It's okay to describe the whole thing by your model of errors.
The claim is that for every circuit that tried, it was within 10 to 20% from the formula.
Yeah, but I'm asking if you use a different error model, does it not does it not still stand?
Sergi, why don't you answer that, and then we had a question from the audience that we'll get to. So
this is a very high level error model, right? When we actually do calibrations and things like that, we tend to use more detailed error models. Now, this error model works, I think, one important reason why it works is because the circuits are random. If the circuits are not random, right, this wouldn't work. Now, the 10 to 20% agreement, that's per circuit. There are a few circuits where we see 25% or whatever, but most of them are below 20%. We do not use the average of the 2-qubit gate errors and error rate and single qubit gate error rate to draw the black line. We actually multiply the error rate per gate. We measure the fidelity of all the different gates, the measurement fidelity for all the different qubits, and we use a slightly more detailed model. I don't think that's very important, but I might have to double check. But when we actually draw the black line, and see an agreement, which is in almost in all cases below 20%. We actually use a slightly more detailed model where we multiply the 2-qubit error rate and single qubit rate of all the different gates. Finally, as I said, the 2-qubit error rates that we use, because we get those numbers running 2-qubit gates on simultaneous mode, it captures errors coming from crosstalk. That's why the 2-qubit error rate in simultaneous mode is around twice as much as if you run a 2-qubit gate with all the other qubits on the ground state. So it introduces some crosstalk, but because we're running random circuits, these crosstalk and possible correlated errors and control errors, there are control errors too. There's 1/f, which is correlated, but the random circuit itself randomizes all those errors, which is why this formula works. And if you're going to be running, a circuit which is not random, then you're going to have to be very careful and introduce dynamical decoupling or randomization or gauges or something else. Because if not, you're going to get worse performance.
I think our question was retracted, so.
I mean, it is maybe a way of summarizing this whole debate of errors, just that, the data is consistent with the simple noise model. So it's, if you believe a simple noise model, this is necessary but not sufficient to demonstrate it. So the whole debate is just kind of revealing our own personal levels of optimism or pessimism, perhaps, about whether this is what's happening underlying.
I would just like to ask if it sounds like this equation 77 is the only issue and the main issue in this work, and I was wondering if that's the case or if there are other important
Or we're
things
getting
in this work.
sidetracked.
Also, equation 69.
These 76 other equations.
It depends. Well, or the other. It depends whom you ask, because for many people there are no other issues. I think no. I just when I prepared my presentation, I just concentrated on one thing. But this is right now. This is look like a fairly important subject. I think we all think it should be cleared out. It's not only our prior. We need to study what happened in reliability of physical systems or engineering systems. This is not something we invented today. And as far as I know, this is unusual behavior, but I don't know so much. And there might be other issues. As I said, we want to understand what is the noisy model. As Umi said, we want to understand if the noisy model is the very simple thing that you mixed the uniform model with the ideal model, or are there some more delicate correction? This is not all the things are criticism of the work. Some of it is we just want to understand what's going on. And I think the one meta-criticism is that the amount of information they give is very, very minimal and very, very suited to this long jump extrapolation to supremacy for 53 qubits. And usually if you want to build such a bridge between what we can do and what we need to predict, you should make much more experiment in the place where we can check matters. But this criticism is not fatal. They can still run more experiment.
Okay, so let me just reiterate the question, and maybe some of the folks coming in virtually can answer. Are there other reasons for skepticism besides this independence question? I think, is that basically what I heard the question to be?
Well, I mean, one of the things that I worry about is, if random quantum circuits turn out just not to be that hard classically. I don't see any reason why they would be classically easy. But if you look at the complexity theoretic hardness results that we've been able to show, they're not nearly as satisfying as they should be. We can show things like, if you will grant that it is hard to estimate an amplitude in a given quantum circuit, even just a little bit better than the trivial estimator, would do. That just always guesses the same thing. then it follows that it is also classically hard to spoof the linear cross entropy benchmark that Google is applying. So we can say that at least there is sort of nothing especially easy to spoof about this linear cross entropy benchmark, but only under a hardness assumption that itself talks about random quantum circuits. And so Umesh and Adam and I guess Bill Pfefferman and Chinmay Nurki have a beautiful result that like a random amplitude in a random quantum circuit is a sharp P complete to calculate. Okay, but we would like to really have results, about even estimating the amplitudes, and and just based on a complexity assumption that is not about random quantum circuits, to just be able to derive that classically spoofing the behavior of a random quantum circuit is a hard problem.
Yeah, I think that the weakest point potentially could be the classical part of the paper, where maybe we'll discover some clever classical algorithm that manages to achieve this. But in some sense, again, if this algorithm is very clever, it might not apply to other things. So it does seem like we have entered the era of quantum supremacy one way or the other. And even if this particular experiment can be matched classically, it does seem we have entered the era, but we're still waiting for the era of first useful quantum systems that solve something that you actually want to solve, and the second is the full fault-tolerant scalable BQP.
All right, we have one question, and maybe this should be the last question since we're nearing the end of our time. So let's.
This is a question for Sergio. I'd like to know if you think that theory should be more adapted to the actual architecture of qubits in the lab, and not just the error models, but also the protocols and algorithms with a small number of qubits.
Should I answer? Okay. I feel like it's ironic that sort of eventually, none of this stuff should matter, right? Like you could say, eventually we hope that a quantum computer programmer or algorithm designer or protocol designer won't need to know more about the underlying hardware than a classical algorithm designer or a protocol designer knows today. And that was very much the attitude that people took in the 90s and the early 2000s when they were thinking about quantum algorithms. When I first entered this field, right, there were experimentalists, but they were working on problems that seemed almost totally orthogonal to what we cared about. Now, the push for quantum supremacy has been a really remarkable example of where theory and experiment have come together, and they've done so out of necessity, right? Out of the desire to achieve this specific goal with hardware that we have today, right? And so what happened was that we had some proposals like the IQP proposal of Bremner, Jozsa, and Shepard, the boson sampling proposal by me and Alex Arkhipov a decade ago. And these were for various interesting architectures, that ended up not being the thing that Google pursued, at the 53 qubit level. But then, we had a discussion about this around 2015, and what we realized was that we sort of came to a consensus at that time that Google should pursue the experiment that makes the most sense for them at the hardware level, and it will be easier for us to adapt the theory to the thing that they're doing than for them to change their whole experiment. Theorists are just a lot cheaper, right? And and importantly, sort of the basic principles in play here, that you take a random quantum circuit, you look at its output distribution, you compute some measure of goodness of the output, that you observe. You check that with a brute force classical computation, and so on and so on, right? These are very general, and these turned out to be adaptable to a very wide range of architectures, including, a 2D grid of qubits with nearest neighbor interactions, which is, of course, what Google ended up building. And so then, like by 2017 or so, Weijie Chen and I, for example, were studying Google's specific architecture, in the papers that we were writing at that time. Although, again, I think the basic conclusions, would have held, not just for that architecture, but for, almost any reasonable architecture. But, but by then we sort of understood what the target was.
All right. Well, shall we thank our panelists, both those present and those abroad? Yes. And for those in attendance, we have pizza and beer in the lobby. Unfortunately, for those in California and Texas, we do not. So, but it's early in the morning for a beer anyway. So, but thank you for joining us.
Thanks a lot, Sergio and Umesh and Scott.
Yeah.
All right. Thanks for having me.
Thank you.
Thanks for.
Good morning.
Very nice.